So two more lessons to go. 6.3 is a little intro into complex numbers. You probably have seen this in Algebra 2, so we will review. But remember, when you have a quadratic equation like this, x squared equals -1, if you take the square root of both sides, the square root of -1 does not yield a real number solution. So they gave it a special number and they say, okay, well, we're going to say let the square root of -1 be something different. We're going to call it I. So this is the imaginary number. Now complex numbers, they can take on the form a plus bi. So you have a real part, and that's what we will call the real part, and bi is the imaginary part. And a and b are real numbers, so we can say a and b are elements. They can be any real number. So an example of a complex number, all of the real numbers are complex numbers, because if you think about it, suppose that a is equal to 1. So b, if b is equal to 0, 1 plus 0i, well, that's a complex number. It's also equivalent to 1. So that's another property. 0 times I is equal to 0. Okay? And you can also just have the imaginary part of a real number. Suppose a is equal to 0, b is equal to 2. So you could do 0 plus 2i, or just 2i. So you can have a real part, and remember, reals are subsets of the complex, and then this is the imaginary part. So just every complex number has a real part and an imaginary part. These are some properties of complex numbers. Now, I don't really want you to memorize these. Some of them, it's just they're nice and handy to have, but you don't really need to know like these. I would expect you to just be able to derive them, and they do that in the formula. This is from FOIL, and so you can see it below. They multiply it out. And the one property that you should put in here, if you know that I is equivalent to square root of -1, then if we square both sides, the square root of -1 squared is equal to -1. So that implies that I squared goes back to a real number. It's -1. So anytime you get a square and I squared when you're working on these problems, you can say that you can substitute -1 into it, and you'll find that. The big deal with number 6 is what they're doing is they're multiplying by what's called the conjugate. So if you have a complex number c plus di, and I multiply by the conjugate of that, and the way that the text talks about that, the conjugate of that would be written as c plus di with a hat over it, a line. So the conjugate is you take your real part and your imaginary part, and you do not change those signs, but rather than a plus, you put a minus. So if we FOIL this out, what's happening is c times c is c squared, c minus di is c di, minus c di, and this times this is plus c di. And this times this is di squared, and it's minus di squared. D squared, excuse me, d times d is d squared, I times that. So then I'm left with, see how these cancel out. That's what's also the difference of squares, if you recall, x plus y times x minus y, and if you FOIL that out, that's just x squared minus y squared. But the reason why we get a plus is now we have c squared minus d squared times I squared is -1. So that's equivalent to c squared, whoops, c squared plus d squared, because of this negative here and this minus here. So that's a way, if you multiply by the conjugate, that's a way to get a real number, because remember, c and d, we're assuming those are the real numbers, and there isn't an I anymore because we squared it out and it becomes -1. So remember, all of these c and d, these are, d is the coefficient of I and c is just the real part. Those are real numbers. Okay, so for the first few examples, I'm going to just do the first problems that you guys will have to do some odds, and all of the answers are in the back so that you can check them. So some of the evens, it's just operations of complex numbers. Remember, these are the real parts here and here. And the imaginary parts are the 3i and the negative 2i. So this is really similar to if I had something like 2 plus 3x parentheses minus negative 3 minus 2x. So what would I do? I would combine the constants, or the numbers without the variables, and it would be 2 plus 3x, and I would clean up this negative, distribute it, change the signs on the inside, plus 3 plus 2x, and then combine like terms. Like terms are the constants, which is 5, and 3x. These are similar terms because they have 1 to the power of 1, and it's x, the variable, and I add the coefficients. So 3 plus 2 is 5x. So the same for this, only you combine the imaginary parts together and the real parts together. So we have 2 plus 3i plus 3, because I'm changing the signs, plus 2i. I'm going to combine the real parts. I'll do a different symbol. That's 2 plus 3 is 5. And I'm going to combine the imaginary parts. 3i plus 2i is 5i. Okay, number 4, the deal is when it's kind of like simplifying a quotient. You want the denominator, usually it's like rationalizing a denominator, you want the denominator to be a real number. So what we're going to do is we're going to multiply by the conjugate, which is, you can write it, I just want you to get comfortable of this, which is equal to, um, so we're going to say, I'll say numerator and denominator, top and bottom. I'm going to say for shorthand. So the conjugate of negative 3 minus 2ai. Now the confusing part is that students will change that negative 3 to a positive 3, but you write your real part is still negative 3, your imaginary part is 2i, but you change that sign. That's the conjugate. So I'm going to multiply the bottom by negative 3 minus 2i, and I'm going to multiply. If you do it to the bottom, you have to do it to the top, because essentially, remember, I'm just multiplying by 1 here because it's the same thing. Okay, so now I'm going to just use FOIL, and if you happen to forget, there's nothing to memorize, it's just FOILing it out. Negative 3 times negative 3 is positive 9. Negative 3 times negative 2i is plus 6i, and let's see, negative 3 times negative 2i is positive. Oh, look at what I did. This is plus, because I was thinking, oh gosh, they have to cancel out. Why aren't they? So this is a negative actually. So change the conjugate is plus here. So I needed to write that plus here and here. Teachable moment. So negative 3 times positive 2i is negative 6i, and that's how we're going to get this canceled, because that times that is positive 6i, so my middle terms go away, and negative 2 times positive 2i is minus 4i squared. Over on the top, we're running out of room here. Let's bring this down here. So on the bottom, we end up with 9 plus 4. Remember, I squared is negative 1, so you have negative 4 times negative 1. And if you want to go to that theorem, you can just say that the conjugate, when I multiply it, it's the first real number part and then the coefficient of the second squared. So first part squared plus the second part squared. That's when you multiply by the conjugate. Now if we FOIL this out, 2 times negative 3 is negative 6. 2 times 2i is positive 4i. 3i times negative 3 is negative 9i. 3i times 2i is 6i. Now all of these are little formulas that they gave you in that green box that I showed you, but I think it's just easier to multiply it out. That requires no memorization, just knowledge of algebra. So I'm just checking my work. We've got negative 6i, 4i, negative 9i, and oh, I didn't square it. Good thing I checked it. That's 6i squared. Okay, so on the bottom, the denominator is 13. This right here, I'm going to just write it as negative 6, because I squared is negative 1. So negative 6 and negative 6, that gives me negative 12. 4i minus 9i is minus 5i. And that's it. Okay, so number 6, they're telling you to write the conjugate first. So what's the conjugate of 2 plus 3i? It's 2 minus 3i. And then it would be minus, keep your parentheses, negative 3 plus 2i. Remember, once again, this stays the same, this stays the same, but this is the only thing that changes, so it changes to a plus. So now I can just do a little distribution of the negative, change those signs. So it's 2 minus 3i plus 3 minus 2i. 2 plus 3 is 5 minus 5i. Okay, to help you with 9, 11, 13, and 15, I just want to look at the pattern of I. So if you have I, well, that's all. We know that it's equal to the square root of negative 1. You can't really do much with that. I squared then, if you square that, we said that's equal to negative 1. What about I cubed? Well, I cubed, I can write that as I squared times I. Remember, you're just adding exponents. 2 plus 1 is 3. I know that I squared is equal to negative 1, and then I have just I, so this is equivalent to negative I. What about I to the fourth? I to the fourth is the same as I squared and I squared. So I squared is equivalent to negative 1, and I have another negative 1. Two negatives make a positive, and I'm left with positive 1. If you have I to the fifth, well, we know from the previous example that it's 1, but I could still break it down like this. I squared times I. That's equivalent to negative 1 times negative 1 times I, so that's positive I. I to the sixth, well, that's I squared, I squared, I squared, and that's equivalent to I negative 1 times negative 1 times negative 1. These make positive, and this gives me just negative 1. So what would I to the seventh be? Well, you could use that idea of negative 1 for I to the sixth times another I. So you have negative 1 times I, so it's just negative I. So it takes 4 basically revolutions to get back to negative I. So 1, 2, 3, 4. So that's the pattern. And they ask you one challenging one. Well, I guess that's number 16, but maybe just as a challenge, think about how you could figure out, without breaking it down like the way I did it, I to the 2009, and figure out what that would be. So just playing around with it. Hopefully you paused the video and tried that out. But if you think about it, I could break it down as I to the 2008 times I to the first. And I kind of expanded. If you wrote I to the second, notice that breaking that up by 2's, that's 1,004 times. Well, that's an even number of negative 1's, which means all of those negative 1's cancel each other out. So I'm just left with I.